So here's something worth thinking about as you settle in tonight. Every single number you've ever seen, on a clock, on a price tag, on the screen of your phone, every one of those numbers had to be invented. Somebody, somewhere, thousands of years ago, had to look at the world and decide that the things in it could be counted. And then they had to figure out how to write that count down. That's not obvious. That's not something the universe just hands you. The animals don't count. The rivers don't count. The stars don't sit up there in the sky with little labels on them saying, "I'm the 407th star from the left." Counting is a human thing, maybe one of the most human things we ever did. And tonight we're going to trace how it happened, slowly, gently, from the very beginning, and follow the thread of mathematics from those first scratches on bone all the way through to the ideas that shaped the modern world. But let's not rush. Let's start where it actually started, which is a place so far back in time that we don't even have writing to tell us about it. We have bones, literal bones. There's an artifact called the Ishango bone. It was found in 1960 by a Belgian geologist named Jean de Heinzelin near the headwaters of the Nile in what is now the Democratic Republic of the Congo. It's a small bone, a baboon's fibula, actually, and it's about 20,000 years old, maybe older, and carved into it are a series of notches, grouped in patterns, 3 columns of marks. Some groups of marks are clearly related. There are groups that seem to pair up, groups that add to 10, groups that add to other groups. Now, there's been a lot of debate about what exactly the Ishango bone represents. Some people think it's a lunar calendar. Some people think it's a tally stick. Some people think the groupings show an awareness of prime numbers, which would be extraordinary for something carved 20,000 years ago. The honest answer is, we're not entirely sure. But here's what we can say with confidence. Whoever carved those notches was thinking mathematically. They weren't just scratching randomly. They were organizing quantity. They were imposing structure on the world. And that's the seed. That's where it all begins. Not with equations, not with proofs, not with any of the things we associate with mathematics today. It begins with a person holding a bone and a sharp stone, making marks, keeping track. Think about what that means. Before you can do mathematics, you need the idea that things can be grouped, compared, and recorded. You need the concept of more and less. You need the concept of same. And those concepts are so deeply embedded in the way we think now that it's hard to imagine a time when they were new. But they were new once. The Ishango bone isn't alone, by the way. There's another artifact, even older, called the Lubombo bone, found in the Lubombo Mountains of Swaziland, or Eswatini as it's known today. That one is about 43,000 years old. It's also a baboon fibula, also covered in notches, 29 of them, which has led some researchers to suggest it might have been used to track a lunar cycle, since the moon's cycle is roughly 29.5 days. 43,000 years. That's staggering. That means humans were engaging in some form of mathematical thinking before the last ice age, before the cave paintings at Lascaux, before we had agriculture, before we had cities, before we had anything that we would recognize as civilization. So, mathematics doesn't begin with civilization. Mathematics begins before civilization. It might even be one of the things that made civilization possible. Let's sit with that for a moment. Because the jump from tally marks on a bone to the mathematics that built the pyramids, that jump is enormous, and it didn't happen overnight. It happened over thousands of years, in fits and starts, in different places around the world, often independently. And the thing that drove it, The engine behind all of it was need. People didn't develop mathematics because they thought it was elegant or beautiful. That appreciation came later. They developed it because they needed to solve problems. How much grain do I have? How much do I owe you? How big is this field? When will the river flood? And that brings us to Mesopotamia, to the land between the rivers, the Tigris and the Euphrates, in what is now Iraq. Around 5,000 years ago, give or take, the Sumerians were building one of the world's first complex civilizations. They had cities, they had temples, they had irrigation systems, they had trade networks that stretched hundreds of miles, and all of that required bookkeeping, serious bookkeeping. You can't run a temple economy where the temple collects grain from farmers, stores it, redistributes it to workers, and trades the surplus without some way of keeping track of quantities. And so, the Sumerians developed one of the earliest number systems we know of. Here's the thing about the Sumerian system. It wasn't like ours. We use base 10. We count in groups of 10, probably because we have 10 fingers. The Sumerians used base 60. Sexagesimal, it's called. And if that sounds bizarre, consider this. You still use it every single day. There are 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. That's all Sumerian. That's a 5,000-year-old counting system that's still embedded in the way you tell time and measure angles right now, tonight, as you're lying there listening to this. Why base 60? Nobody knows for certain. One theory is that 60 is an incredibly convenient number because it has so many divisors. You can divide 60 evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That makes it fantastic for dividing things up, splitting rations, dividing land, portioning out trade goods. If you're running a complex economy and you need to split quantities into halves, thirds, quarters, fifths, and sixths without getting messy fractions, base 60 is a brilliant choice. Whether the Sumerians chose it deliberately for that reason, or whether it evolved from merging two earlier systems, maybe a base 5 finger counting system and a base 12 system based on counting the segments of your 4 non-thumb fingers, that's still debated. But the result was a number system of remarkable flexibility. And the Sumerians didn't just count. They calculated. We know this because they left behind tens of thousands of clay tablets, pressed with a reed stylus into soft clay and then baked hard. Many of these tablets are administrative records, lists of sheep, quantities of barley, land measurements, but some of them are clearly mathematical exercises. Multiplication tables, tables of reciprocals, which is how they handled division, by multiplying by the reciprocal instead. Lists of squares and cubes. These were school tablets, made by students learning their trade in scribal schools called edubas. Imagine that. 4,000 years ago, there were kids sitting in classrooms, practicing their multiplication tables on clay, probably just as reluctantly as kids do today. The Babylonians, who came after the Sumerians and inherited their mathematical tradition, took things even further. And this is where it gets really interesting. By about 1800 BCE, Babylonian mathematicians, and they really were mathematicians, even if they wouldn't have used that word, were solving what we would call quadratic equations. They could handle problems that we'd write today as x squared, plus some number times x equals some other number. They didn't write it that way, of course. They didn't have algebra in the symbolic sense. They described everything in words and worked through procedures, step by step, almost like recipes. Take half of the coefficient, square it, add it to the right side, take the square root. They had systematic methods, algorithms essentially. The word algorithm itself comes from a mathematician's name, but we'll get to that later. One of the most famous Babylonian tablets is called Plimpton 322. It's a small clay tablet about the size of your hand, dating to roughly 1800 BCE, and it contains a table of numbers that correspond to what we call Pythagorean triples, sets of 3 whole numbers, where the square of one equals the sum of the squares of the other two. 3, 4, 5 is the most famous one. 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. The tablet lists 15 of these triples, some of them quite large, and the precision and organization suggest a deep understanding of the relationships between these numbers. This is more than 1,000 years before Pythagoras was born. 1,000 years. So when we call them Pythagorean triples, we're crediting the wrong civilization, which happens a lot in the history of mathematics, honestly. Now, let's pause here and think about what the Babylonians were actually doing with this knowledge, because it wasn't abstract. They were surveyors. They were builders. They were engineers, in a very real sense. When the Euphrates flooded, and it flooded regularly, which was both a blessing and a catastrophe, it would wash away field boundaries. And after the waters receded, someone had to go out and remeasure the fields, re-establish who owned what, figure out the areas for tax purposes. That requires geometry. Real practical geometry. You need to measure lengths, calculate areas, handle right angles. If you're laying out a rectangular field and you want to make sure the corners are actually square, knowing that a 3-4-5 triangle gives you a perfect right angle is incredibly useful. You measure 3 units along one side, 4 units along the other, and if the diagonal is exactly 5, your corner is square. Builders still use this trick today. Carpenters call it the 3-4-5 rule. So mathematics, at this stage, is deeply practical. It's about land and grain and commerce and construction. It's about solving the problems that arise when thousands of people live together in cities and need systems to manage resources. And the people doing this work were valued. Scribes who could calculate were essential to the functioning of the state. They were the accountants, the engineers, the civil servants of the ancient world. But here's what's quietly remarkable about the Babylonian mathematical tablets. Some of them go beyond what's strictly necessary. Some of them explore problems that don't have obvious practical applications. There are tablets that calculate the square root of 2 to extraordinary precision. The famous Yale tablet, YBC 7289, gives the square root of 2 as something like 1.414213, which is accurate to about 6 decimal places. That's not a practical necessity. Nobody needs the square root of 2 to 6 decimal places to measure a field. That's curiosity. That's someone pushing the mathematics further than they need to, just to see how far it goes. And that impulse, that desire to know not because you have to, but because you want to, that's the spark that will eventually transform mathematics from a practical tool into something much deeper. Meanwhile, something similar was happening along the Nile. The Egyptians were developing their own mathematical tradition, shaped by their own needs, their own landscape, their own engineering ambitions. And oh, what ambitions they were, because the Egyptians were building the pyramids. The Great Pyramid of Giza was constructed around 2560 BCE, and the mathematics required to build it, to plan it, to survey the site, to cut and transport and place roughly 2.3 million stone blocks with the precision they achieved, that mathematics had to be solid. The base of the Great Pyramid is almost perfectly square. The sides are aligned to the cardinal directions with an accuracy of about 1/12 of a degree. The difference in length between the longest and shortest sides of the base is less than 8 inches across a span of over 750 feet. That's extraordinary precision for any era, let alone for a civilization working without telescopes, without steel measuring tapes, without any of the tools we take for granted. How did they do it? Well, we know some of it from a document called the Rund Mathematical Papyrus, which is one of the most important sources we have for understanding Egyptian mathematics. It was written around 1550 BCE by a scribe named Ahmes, one of the earliest named mathematicians in history. And he noted that he was copying from an even older document, dating to perhaps 1850 BCE. The papyrus contains 84 mathematical problems and their solutions, covering arithmetic, fractions, geometry, and even some early algebra. And the way the Egyptians handled fractions is fascinating and a little bit maddening because they insisted on using only unit fractions with a numerator of 1. So instead of writing 3/4, they'd write 1/2 plus 1/4. Instead of 2/5, they'd write 1/3 plus 1/15. They had elaborate tables for decomposing fractions this way, and while it seems cumbersome to us, it worked for them for over 1,000 years. The Rhind papyrus also shows us how the Egyptians calculated the area of a circle, and this is where something beautiful emerges. Their method was to take the diameter of the circle, subtract 1/9 of it, and square the result. If you work through the math, this is equivalent to using a value of pi, the ratio of a circle's circumference to its diameter, of about 3.16. Not bad at all. The actual value is 3.14159 and change, so the Egyptian approximation is off by less than 1%. Good enough to build pyramids, certainly. Good enough to lay out circular granaries and calculate how much grain they could hold. And speaking of pi, this is one of those numbers that's going to keep coming back throughout our story tonight, because the history of pi is in many ways the history of mathematics itself. A number that seems simple, the ratio of a circle's circumference to its diameter, but turns out to be infinitely complex, irrational, transcendental, full of surprises that mathematicians are still exploring today. The Egyptians approximated it. The Babylonians used a cruder value of about 3, or sometimes 3 1/8, and over in another part of the world entirely, along the banks of the Indus River, yet another civilization was developing its own relationship with numbers and measurement, one that would eventually produce some of the most profound mathematical innovations in human history. The Indus Valley civilization, with its astonishingly well-planned cities, Mohenjo-Daro, Harappa, laid out on precise grids with standardized brick sizes and sophisticated drainage systems, clearly had mathematical knowledge that we're only beginning to appreciate. And here's the frustrating thing. The Indus Valley civilization used a script that we still haven't deciphered, not for lack of trying. Scholars have been staring at those symbols for the better part of a century, and we just can't crack them. Not yet, anyway. So, unlike the Babylonians with their cuneiform tablets full of multiplication tables, or the Egyptians with the Rhind papyrus spelling out fraction problems, the Indus Valley people left us their cities, their artifacts, their extraordinary infrastructure, but not, in any readable form, their mathematical writings. What we know, we have to infer from what they built. And what they built tells us a lot. Those standardized bricks, for instance, they follow a consistent ratio of roughly 1 to 2 to 4. Length, width, height. That ratio shows up across different cities separated by hundreds of miles. Think about what that implies. It means There was some kind of centralized system of measurement, some agreed-upon standard, being communicated and enforced across a vast geographic area. The bricks at Mohenjo-Daro match the bricks at Harappa, and Harappa is about 600 kilometers away. You don't get that kind of consistency by accident. Someone, somewhere, was defining units, and those units were being transmitted and maintained with remarkable fidelity. They also had a sophisticated system of weights. Archaeologists have found hundreds of polished stone cubes that follow a binary decimal progression. The smallest weights double in sequence: 1, 2, 4, 8, 16, 32, 64, and then at higher values, the system shifts to decimal multiples. It's clever. The smallest weight is about 0.87 grams, and the ratios hold with impressive precision. These weren't rough approximations. These were carefully manufactured measurement tools, which means they had a deep practical grasp of ratio and proportion, even if we can't read whatever notation they use to express it. The urban planning alone is stunning. The streets of Mohenjo-Daro intersect at right angles. The drainage system, and this always amazes me, the drainage system rivals some modern cities. Every house had a connection to a covered main drain running beneath the street. The gradients had to be calculated so that water would flow properly. That's applied mathematics, pure and simple. Slope, volume, flow rate. Someone was doing those calculations, and doing them well. But because we can't read their writing, the Indus Valley civilization remains this tantalizing shadow in the history of mathematics. We can see the results of their knowledge everywhere in the archaeological record, but the knowledge itself, the methods, the notation, the way they taught it, all of that is, for now, lost to us. It's one of the great unsolved puzzles of ancient history. Maybe someday someone will crack that script, and a whole new chapter of mathematical history will open up. For now, though, we have to let the bricks and the weights and the perfectly graded drains speak for themselves. So let's shift our gaze east, because the Indian subcontinent's mathematical story doesn't end with the Indus Valley. Far from it. In fact, it's just getting started. After the decline of the Indus Valley civilization around 1900 BCE, and the reasons for that decline are themselves debated, possibly climate change, possibly shifts in river courses, the mathematical tradition continues and eventually flourishes in ways that will reshape the entire world. The Vedic period, roughly 1500 to 500 BCE, gives us the Sulba Sutras, which are appendices to the Vedas, the ancient religious texts. The Sulba Sutras are essentially manuals for constructing sacrificial altars, and that sounds very specific, and maybe not that exciting, but here's the thing. To build these altars correctly, you needed some seriously sophisticated geometry. The altars had to be precise shapes and precise areas. Some had to be constructed so that one altar had exactly the same area as another altar of a completely different shape. Imagine being told, build me a circular altar that has exactly the same area as that square one over there. That's a deep geometric problem, and the Sulba Sutras tackle it. They contain clear statements of what we call the Pythagorean theorem, the relationship between the sides of a right triangle. And remember, this is independent of Pythagoras, who won't come along until around 500 BCE. The Baudhayana Sulba Sutra, dating to perhaps 800 BCE, states the theorem explicitly. It also gives a remarkably good approximation of the square root of 2. 1 plus 1/3 plus 1 over 3 times 4 minus 1 over 3 times 4 times 34, which works out to about 1.4142156, compared to the actual value of 1.4142135. That's accurate to 5 decimal places. And just like that tablet from Babylon, YBC 7289, here's another ancient civilization arriving at essentially the same value through its own methods, for its own reasons. Now, I want to pause on something here, because it's worth sitting with. We've got the Babylonians around 1800 BCE knowing the Pythagorean relationship and computing the square root of 2 to extraordinary precision. We've got the Indians, independently, doing essentially the same thing centuries later in the context of altar construction, and eventually we'll get to Pythagoras and the Greeks, who will get all the credit in the Western tradition. The theorem that bears Pythagoras's name was known to at least 2 other civilizations before him. That doesn't diminish what Pythagoras and his followers did. They brought something new to the table, which we'll get to. But it's a good reminder that mathematical ideas often arise independently in different cultures, driven by different needs. The Babylonians needed to survey flooded fields. The Indians needed to build sacred altars. The geometry doesn't care why you need it. It's there, waiting to be found, and different people in different places keep finding it. So let's talk about the Greeks, because this is where the story takes a dramatic turn. Not because the Greeks were better mathematicians than the Babylonians or the Egyptians or the Indians. In many practical respects, they weren't. But because the Greeks did something that, as far as we know, nobody had done before. They asked why. The Babylonians could solve quadratic equations. They had procedures, recipes, step-by-step algorithms that worked beautifully, but they didn't seem to ask, or at least they didn't write down, why those procedures worked. The Egyptians could calculate the area of a circle with impressive accuracy, but they didn't prove that their method was correct, or explore the deeper properties of circles that made the method work. The earlier mathematical traditions were, broadly speaking, computational and practical. Here's a problem. Here's how you solve it. Here's the answer. And that's enormously valuable. That built civilizations. But the Greeks, starting around the 6th century BCE, began to insist on something more. They wanted proof. They wanted to know, not just that something was true, but why it was true, and to demonstrate that truth through logical reasoning from basic assumptions. And this shift, from calculation to proof, from recipe to theorem, is one of the most consequential intellectual developments in human history. The person traditionally credited with starting this revolution is Thales of Miletus, who lived around 624 to 546 BCE. Miletus was a Greek city on the coast of what's now Turkey, a prosperous trading hub where ideas from Egypt, Babylon, and the broader Mediterranean world all mingled. Thales reportedly traveled to Egypt and learned geometry there, but when he brought it back to the Greek world, he did something different with it. He began to prove geometric propositions. He's credited with demonstrating that a circle is bisected by its diameter, that the base angles of an isosceles triangle are equal, that vertical angles are equal. These might sound obvious to you, and in a way they are. But the point isn't whether they're obvious. The point is that Thales insisted on demonstrating them through logical argument, rather than just asserting them or showing that they worked in specific cases. This is a subtle but profound shift. When the Babylonians showed that their method for solving a quadratic equation gave the right answer, they were doing something like what we'd call verification, checking that the answer works. When Thales proved that the base angles of an isosceles triangle must be equal, he was doing something different. He was showing that it couldn't be otherwise, that it followed necessarily from the basic properties of lines and angles. That's a different kind of knowledge. It's the difference between knowing that something is true and understanding why it must be true. Now, we should be a little careful here, because almost everything we know about Thales comes from much later sources. He didn't leave any writings that survive. Later, Greek authors attributed these proofs to him, but the details are hazy. Some historians think Thales has been somewhat mythologized, turned into a founding figure who's a bit larger than life. That's probably fair. But even if the specific attributions are uncertain, the broader point stands. Something changed in the Greek mathematical world around this time. A new emphasis on deductive reasoning, on proof, on understanding the logical structure behind the calculations. And then comes Pythagoras, born around 570 BCE on the island of Samos. Pythagoras is one of those figures who's become almost more myth than man. He founded a secretive, philosophical, and mathematical community in southern Italy, in the city of Croton. The Pythagoreans were part school, part religious brotherhood, part philosophical commune. They believed that numbers were the fundamental reality underlying all of existence, that the universe, at its deepest level, was made of mathematics. All is number, they supposedly declared. And you know what? In a strange way, modern physics has circled back to something surprisingly close to that view. But we're getting ahead of ourselves. The Pythagoreans studied the properties of whole numbers with an almost mystical devotion. They classified numbers as perfect, abundant, or deficient, based on the sum of their divisors. A perfect number is one where the divisors add up to the number itself. 6 is the smallest because 1 plus 2 plus 3 equals 6. The next one is 28. They found these relationships beautiful, even sacred. They discovered that musical harmony was connected to simple numerical ratios. Pluck a string, then pluck a string half as long, and you get a note exactly 1 octave higher. The ratio 2 to 1. A ratio of 3 to 2 gives you a perfect fifth. This was, to the Pythagoreans, evidence that the universe was fundamentally mathematical, that beauty and harmony and number were all expressions of the same underlying truth. And then they discovered something that shook their worldview to its foundations, something so disturbing that, according to legend, they tried to keep it secret. The story goes that a Pythagorean named Hippasus made the discovery and was either expelled from the community or, in some darker versions of the tale, drowned at sea as divine punishment. The discovery was this: the square root of 2 is irrational. It cannot be expressed as a ratio of 2 whole numbers. No fraction, no matter how complicated, will ever exactly equal the square root of 2. And if all is number, and by number you mean whole numbers and their ratios, then here was a quantity, a perfectly natural, geometrically obvious quantity, just the diagonal of a unit square, that fell outside your entire system. It was a crisis. The Pythagoreans had built their philosophy on the idea that everything could be expressed through whole number ratios, and here was proof that it couldn't. Think about how unsettling that must have been. You've devoted your life to the belief that the universe is built on the harmony of whole numbers, and then you discover that something as simple as the diagonal of a square refuses to fit. It's right there in front of you, this diagonal line you can draw with a straight edge, a length you can point to and say, that's real, that exists, and yet your entire number system can't name it. Not approximately, it can never name it exactly. No matter how large the whole numbers you use in your fraction, you will never land precisely on the square root of 2. It's always a little off, always slipping between the cracks. And here's what makes the proof so devastating. It's not even that complicated. The argument Hippasus is credited with, or at least the argument that has come down to us from Greek mathematics, is a proof by contradiction. You start by assuming the opposite of what you want to show. You say, okay, suppose the square root of 2 can be written as a fraction, some whole number divided by another whole number, and let's say we've reduced that fraction to its simplest form. No common factors between the top and bottom. Then you square both sides, and you work through the algebra, and you find that the top number has to be even. But if the top is even, then when you carry that through, the bottom has to be even too. And now you've got a contradiction. You said the fraction was fully reduced, no common factors, but both numbers are even, which means they share a factor of 2. So your original assumption must be wrong. The square root of 2 can't be a fraction. It's irrational. Done. That's it. That's the whole proof. And it's elegant, and it's airtight, and it destroyed a worldview. And what I find so moving about this story, whether or not the details about Hippasus and the drowning are literally true, is that it shows mathematics doing something that almost no other human endeavor does. It forces you to accept truths you don't want to accept. You can't argue your way out of a valid proof. You can't lobby against it, or spin it, or pretend it doesn't exist. The Pythagoreans tried, if the legends are accurate. They tried to suppress it. But the truth of irrational numbers didn't care about their philosophy. It was just true. And this moment, this crisis of the irrational, marks a kind of turning point in the history of mathematics. Because from here forward, Greek mathematics becomes increasingly geometric rather than arithmetic. If you can't trust numbers to behave, if there are lengths that numbers can't express, then maybe geometry is the safer foundation. And that's exactly the direction Greek math went. For the next few centuries, the most sophisticated mathematical thinking in the Greek world was done through geometry, through diagrams and constructions and proofs about shapes, rather than through numerical calculation. This is partly why Greek mathematics looks so different from Babylonian mathematics. The Babylonians were brilliant calculators. They loved numbers. They were comfortable with approximations. They developed algorithms. The Greeks, after the shock of irrational numbers, retreated into the purity of geometric proof, where a line could be as long as it needed to be, without anyone having to write down its exact numerical length. Now, the person who towers over this geometric tradition, the person who essentially codified it for all of Western civilization, is Euclid. And here's something funny about Euclid. We know almost nothing about him as a person. He worked in Alexandria, probably around 300 BCE, and he wrote the Elements. And that's about it. We don't know when he was born, when he died, what he looked like, whether he was tall or short or funny or serious. There's a famous anecdote where a student supposedly asked him what practical use geometry was, and Euclid told a servant to give the student a coin, since he must make a profit from what he learns. That's a great line, but we can't even be sure it really happened. What we can be sure of is the book, the Elements, and the Elements might be the most influential textbook ever written in any subject. It was used as the standard geometry textbook in Europe for over 2,000 years. Abraham Lincoln studied it. It was printed in more editions than almost any book other than the Bible. And what made it so remarkable wasn't that all the results were new. Many of them were known before Euclid. What made it remarkable was the structure. Euclid started with definitions. A point is that which has no part. A line is breadthless length. Then he laid down postulates, basic assumptions that he asked you to accept as self-evidently true. Things like, You can draw a straight line between any 2 points. You can extend a line indefinitely. All right angles are equal. 5 postulates in total. And then, from those 5 postulates and a handful of common notions, he built everything. Proposition by proposition, proof by proof, each result following logically from the ones before it. Triangles, circles, parallel lines, areas, ratios, solid geometry, all of it erected on that tiny foundation of 5 postulates. It was a cathedral of logic, and the architecture was breathtaking. Think about what that means as an intellectual achievement. Euclid was saying, here are 5 things I'm going to assume. That's it. From these 5 seeds, I will grow an entire forest of mathematical truth, and every single tree in that forest can be traced back, step by step, to those 5 seeds. Nothing is taken on faith except those initial postulates. Everything else is proven, and the proofs are so careful, so meticulous, that they hold up 23 centuries later. That's not just mathematics. That's a model for how to think clearly about anything. Now, the 5th postulate is where things get really interesting, and this is a thread that won't fully pay off for another 2,000 years. But let me plant the seed now. The first 4 postulates are simple, clean, almost obvious. But the 5th one, the parallel postulate, is different. It's longer, more complicated, and it feels less like an obvious truth and more like something that ought to be provable from the other 4. Euclid himself seems to have been uneasy about it, because he avoided using it for as long as possible in the Elements, proving the first 28 propositions without it. The 5th postulate, roughly stated, says that if you have a line and a point not on that line, there is exactly one line through that point that is parallel to the original line. Seems reasonable, right? Seems like it should just follow from the other postulates. And for over 2,000 years, mathematicians tried to prove it did. They all failed. But we'll come back to that. That story has a magnificent ending, and it involves the discovery of entirely new kinds of geometry that nobody in Euclid's time could have imagined. But staying in Alexandria for a moment, because Alexandria, in the 3rd century BCE, was extraordinary. It was the intellectual capital of the Mediterranean world, home to the great library, a magnet for scholars from everywhere. And it wasn't just Euclid. Archimedes, who many consider the greatest mathematician of antiquity, had connections to Alexandria, though he spent most of his life in Syracuse, on the island of Sicily. And Archimedes, let's talk about Archimedes, because he's one of those figures where the more you learn about what he actually did, the more astonishing it becomes. Archimedes was born around 287 BCE, and he was, in modern terms, both a mathematician and an engineer. He's famous for the Eureka story. Supposedly, he figured out how to test whether a crown was pure gold by noticing the water displacement when he got into a bath, and he was so excited he ran through the streets, naked, shouting, "Eureka!" which means, "I have found it." That story may be embellished, but the principle of buoyancy it illustrates is real, and it's his. Archimedes' principle, a body immersed in fluid experiences an upward force equal to the weight of the fluid it displaces. That's not just a neat idea. That's the foundation of how we understand why ships float, why submarines work, why hot air balloons rise. But the mathematical work is where Archimedes really shines. He calculated the area under a parabola. He determined the surface area and volume of a sphere, proving that the volume of a sphere is exactly 2/3 the volume of the cylinder that encloses it. He was so proud of this result that he supposedly asked for a sphere inscribed in a cylinder to be engraved on his tombstone. And when the Roman general Cicero found his neglected grave centuries later, that's how he identified it, by the diagram on the stone. And here's where it connects to our old friend pi. Archimedes tackled the problem of calculating pi more rigorously than anyone before him. His method was beautiful in its simplicity. He drew a circle, then inscribed a regular polygon inside it, a polygon whose corners all touched the circle. Then he circumscribed another regular polygon outside the circle, this one just barely containing it. The circle's circumference had to be somewhere between the perimeters of the inner and outer polygons. Start with hexagons, and you get a rough estimate. Double the number of sides to 12-sided polygons, and the estimate gets tighter. Double again to 24 sides, then 48, then 96. Archimedes worked all the way up to 96-sided polygons, doing all the calculations by hand, and he pinned pi down between 223/71 and 22/7. That's between roughly 3.1408 and 3.1429. Remarkable precision for hand calculation in the 3rd century BCE. And what's really profound about his method is that it contains the germ of an idea that wouldn't be fully developed for almost 2,000 years. The idea of a limit. Each time you double the number of sides, the polygons get closer and closer to the circle. They never become the circle, but they approach it, squeezing it from both sides with increasing precision. That's the intuition behind calculus, and Archimedes was dancing right at its edge. He even used a technique called the method of exhaustion, which is essentially integration before integration had a name. He would fill an area with smaller and smaller shapes, exhausting the space between his approximation and the true area, proving that the difference could be made smaller than any given quantity. That's a limit argument. That's the epsilon-delta reasoning that wouldn't be formalized until the 19th century, and here was Archimedes doing it with geometric diagrams in ancient Syracuse. There's actually a document called the Archimedes palimpsest that makes this even more remarkable. In 1906, a Danish scholar named Johann Ludwig Heiberg discovered a medieval prayer book in Constantinople that turned out to be written on recycled parchment. Underneath the prayers, scraped away but still faintly legible, were works by Archimedes, including a text called The Method, which had been lost for centuries. And in The Method, Archimedes described how he actually discovered his results, as opposed to how he formally proved them. And his discovery method involved slicing shapes into infinitely thin strips and balancing them on a lever, essentially using physical intuition about centers of gravity to do what we would now call integration. He knew this wasn't rigorous by Greek standards, which is why he then went back and proved everything formally using the method of exhaustion. But the fact that he was thinking in terms of infinitesimals, in terms of infinitely thin slices, in the 3rd century BCE, it's staggering. He was closer to inventing calculus than anyone would be again for nearly 2 millennia. And then there's the way he died, which tells you something about both the man and the precariousness of knowledge. In 212 BCE, the Romans besieged Syracuse. Archimedes, by then an old man, had designed war machines to defend the city, giant cranes that could lift ships out of the water, catapults, possibly even focused mirrors to set ships on fire, though that last one is debated. But Syracuse fell. And according to the most famous version of the story, a Roman soldier found Archimedes drawing geometric diagrams in the sand. The soldier ordered him to come along. Archimedes, absorbed in his work, reportedly said something like, "Do not disturb my circles." The soldier killed him. The Roman general Marcellus, who had given orders that Archimedes should not be harmed, was supposedly grief-stricken. But the damage was done. one of the greatest minds in human history, cut short by a soldier who didn't know or care what he was interrupting. And that loss echoes forward through time, because we have to wonder, what else did Archimedes know that we've lost? The palimpsest was a lucky recovery, but how many other texts were scraped clean, burned, rotted away? How much further along might mathematics have been if Archimedes had lived another decade, or if his full body of work had survived intact? It's one of those questions that haunts the history of science, and it connects to a larger pattern we'll see again and again. Knowledge is fragile. It can be created by a single brilliant mind and destroyed by a single act of violence or neglect. The continuity of mathematical progress that we sometimes take for granted, this idea that knowledge only moves forward, accumulates, builds on itself, that's not guaranteed. It has to be actively preserved, copied, translated, taught. And when those chains of transmission break, centuries of progress can simply vanish. And that's exactly what happened. The centuries after Archimedes' death are a strange, bittersweet period in the history of mathematics. Because the work didn't stop entirely. There were brilliant people still pushing ideas forward in the Hellenistic world. But the momentum shifted, and the center of gravity began to move in ways that would reshape everything. Let's stay in Alexandria for a moment, because that city matters enormously to this story. Remember, Euclid had worked there around 300 BCE, and the great library of Alexandria had become the intellectual heart of the Mediterranean world. It was, in many ways, the first real research institution, a place where scholars were paid to think, to write, to argue with each other. And in the generations after Archimedes, Alexandria produced mathematicians who were extraordinary in their own right, even if they don't always get the same recognition. Take Apollonius of Perga, who was active around 200 BCE. He wrote a monumental treatise on conic sections, the curves you get when you slice a cone at different angles, an ellipse, a parabola, a hyperbola. Now, those names might sound like abstract geometry class vocabulary, but here's the thing. Those curves turn out to be everywhere in the physical world. The orbit of every planet around the sun is an ellipse. The path of a ball thrown through the air, ignoring air resistance, is a parabola. The shape of a satellite dish or a car headlight reflector is a paraboloid. Apollonius didn't know any of that. He was studying these curves as pure geometry, just fascinated by the shapes themselves and their properties. But nearly 2,000 years later, when Johannes Kepler was trying to figure out how Mars moves through the sky, it was Apollonius's work on ellipses that gave him the mathematical language he needed. That's one of the recurring miracles of mathematics. Someone studies something for its own beauty, and centuries later, it turns out to be exactly the tool someone else needs to unlock the universe. It happens over and over again, and it never stops being a little eerie. Apollonius wrote 8 books on conics. Only the first 4 survive in the original Greek. Books 5 through 7 survive only because they were translated into Arabic centuries later. And book 8 is lost entirely. There it is again, that fragility. We have most of Apollonius' masterwork only because scholars in Baghdad, working in the 9th century, thought it was worth preserving. If they hadn't, we'd have lost half of it. And then there's Hipparchus, working around 150 BCE, who essentially invented trigonometry. Or at least, he created the first known table of chords, a systematic way of relating angles to the lengths of line segments in a circle. If you've ever used sine or cosine, you're using a descendant of what Hipparchus built. He needed it for astronomy,
for predicting where stars and planets would appear in the sky, and his work was later refined and extended by Claudius Ptolemy, working in Alexandria around 150 CE, who compiled the Almagest, this massive astronomical encyclopedia that would remain the definitive reference for over 1,000 years. Ptolemy's chord tables were essentially trigonometric tables, and they were astonishingly accurate. He could predict eclipses, track planetary positions, calculate the apparent size of the moon. All of it built on this mathematical framework of relating angles to ratios. But here's what I want you to notice about this period. The mathematics being done is increasingly practical, increasingly tied to astronomy and engineering and
geography. Eratosthenes, the librarian of Alexandria around 240 BCE, famously calculated the circumference of the Earth using nothing but shadows, angles, and the distance between two cities. And he got it right to within maybe 2% of the actual value. Think about that. A person standing on the surface of the Earth with no satellites, no aircraft, no way to see the curvature directly, figured out the size of the entire planet using geometry and a stick in the ground. That's the power of mathematical reasoning. You don't have to see something to measure it. You just need the right relationships. But alongside this practical brilliance, something was also being lost. The Greek tradition of rigorous proof, that insistence on deductive certainty that Euclid had embodied, was gradually becoming less central, not disappearing, but fading as a priority. The emphasis shifted toward calculation, toward getting answers, toward solving specific problems. And that shift matters because it reflects a deeper tension in mathematics that's still alive today. The tension between pure and applied, between understanding why something is true and just knowing how to use it. Now, as the Roman Empire absorbed the Hellenistic world, mathematics wasn't exactly a Roman priority. The Romans were extraordinary engineers. Their roads, aqueducts, and concrete structures are still standing 2,000 years later. But they were practical people. They used mathematics as a tool, not as a subject of deep inquiry. Roman numerals, which you've seen on clock faces and Super Bowl numbers, are actually terrible for doing arithmetic. Try multiplying 47 by 1,914, and you'll see the problem immediately. The Roman numeral system has no place value, no zero, no efficient way to handle large calculations. Roman engineers and surveyors used counting boards and abacuses to do their actual computing, and the numeral system was mainly for recording results. It's a reminder that notation matters enormously. The symbols you use to write mathematics shape what mathematics you can do. A clumsy notation is like trying to run in heavy boots. You can move, but you can't move fast, and you certainly can't dance. So during the centuries of Roman dominance, from roughly 100 BCE to 400 CE, the mathematical frontier wasn't really in Europe. The most interesting work was happening elsewhere. And this is where we need to talk about two parallel streams of mathematical development that were flowing at the same time, largely independently, and that would eventually converge in one of the most important intellectual transfers in human history. The first stream is India. And here's where the story gets really exciting, because Indian mathematicians were about to give the world something so fundamental, so transformative, that it's hard to imagine modern life without it. They were going to invent the number system we actually use. We talked earlier about the Sulba Sutras and their geometric sophistication. But Indian mathematics kept developing, and by the early centuries of the Common Era, something remarkable was emerging. Indian mathematicians were developing a fully positional decimal number system, meaning a system where the value of a digit depends on its position, using base 10, with a symbol for every digit from 1 through 9. And crucially, and this is the part that changes everything, they invented a symbol for 0. Now, 0 seems obvious to us. Of course there's a 0. It's just nothing, right? But think about how radical this actually is. 0 isn't just the absence of quantity. It's a number in its own right. It's a placeholder that makes positional notation work. It's the difference between 42 and 402 and 420. Without 0, you can't have a clean positional system. The Babylonians, remember, had a positional system in base 60, and for a long time they had no 0 at all. They just left a gap, which was ambiguous and error-prone. They eventually developed a placeholder symbol, but they never quite treated it as a number you could calculate with. The Indian mathematicians did. And the person most associated with crystallizing this system is Brahmagupta, working in Rajasthan around 628 CE. In his book, The Brahmasfuta Siddhanta, Brahmagupta laid out rules for arithmetic with 0. 0 plus a number is that number. A number minus itself is 0. A number times 0 is 0. He even tried to define division by 0 and got that one wrong, or at least got into territory that wouldn't be properly resolved for over 1,000 years. But the ambition is what matters. He was treating 0 as a full citizen of the number system, something you could operate on just like any other number. Brahmagupta also worked extensively with negative numbers, which he called debts, as opposed to fortunes. He laid out rules for multiplying negatives. A debt times a debt is a fortune, which is to say, a negative times a negative is a positive. This was centuries before European mathematicians would become comfortable with negatives. In fact, European mathematicians were still calling negative numbers absurd and fictitious well into the 1500s and beyond. Brahmagupta just used them, pragmatically, clearly, without philosophical hand-wringing. And he wasn't alone. Indian mathematics in this period was flourishing. Aryabhata, working around 499 CE, so a bit before Brahmagupta, had already developed sophisticated methods for calculating square roots, solving certain types of equations, and working with trigonometric functions. Aryabhata's sine tables were remarkably accurate, and his astronomical calculations were impressive. He even suggested that the Earth rotates on its axis, which was a controversial claim at the time. But the decimal place value system with 0, that's the headline. That's the gift that Indian mathematics gave to the world, because once you have that system, arithmetic becomes almost mechanical. Addition, subtraction, multiplication, long division, all of those algorithms that you learned in school, the ones where you line up the digits and carry and borrow, those procedures only work because of positional notation with 0. Try doing long multiplication with Roman numerals. You literally can't. The algorithm doesn't exist in that notation. The notation itself enables the method. So now we have this incredibly powerful number system developing in India, and the question becomes, how does it get from India to the rest of the world? And this is where the second stream comes in, the one flowing through the Islamic world. Because in the 7th and 8th centuries, something extraordinary was happening in the Middle East. The rise of Islam had created a vast civilization stretching from Spain to Central Asia. And within that civilization, there was an astonishing hunger for knowledge. The Abbasid Caliphate, centered in Baghdad, established the Beit al-Hikmah, the House of Wisdom, in the early 9th century. And what happened there is one of the great intellectual stories in human history. The House of Wisdom was a translation center, a library, an academy, all rolled into one. Scholars there, Muslim, Christian, Jewish, Zoroastrian, working side by side, systematically translated Greek, Indian, and Persian texts into Arabic. Euclid's Elements, Ptolemy's Almagest, Apollonius's Conics, the works of Archimedes, the astronomical tables of Indian mathematicians, all of it was translated, studied, commented upon, and extended. This was not mere preservation. This was active, creative engagement with the material. The scholars of the House of Wisdom didn't just copy old knowledge, they transformed it. And the person who stands at the center of this mathematical transformation has a name you might recognize, even if you don't realize it. Muhammad ibn Musa al-Khwarizmi, working in Baghdad around 820 CE. His name is the origin of the word algorithm, and the title of his most famous book, Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, contains a word that became algebra, al-Jabr. It literally means something like the reunion of broken parts, or restoration, and it referred to a specific operation, moving a subtracted quantity to the other side of an equation to make it positive again. That's what al-Jabr meant in its original context. And al-Muqabala, the other key word in the title, meant balancing, canceling like terms on both sides. So the very title of the book is describing two algebraic operations, two moves you make when you're solving an equation. And from that title, from that single Arabic word, we get the entire field we now call algebra. Now, here's what's important about what al-Khwarizmi actually did in this book. He wasn't just collecting problems and showing how to solve them, the way the Babylonians had done over 1,000 years earlier. Remember, the Babylonians could solve quadratic equations. They had recipes, step-by-step procedures. But al-Khwarizmi did something subtly different, something that pushed mathematics forward in a way that's easy to underestimate. He tried to be systematic. He tried to classify. He looked at equations and said, essentially, let me organize all the different types of problems you might encounter and show you a general method for each type. He identified 6 basic forms of linear and quadratic equations. Things like squares equal to roots, squares equal to numbers, roots equal to numbers, and then the 3 mixed cases. And for each type, he gave a general procedure, not just a specific example with specific numbers, but a method that works for any equation of that form. He wrote it all out in words, by the way. No symbols, no x's and y's. Everything was rhetorical algebra, written out in complete sentences. The square plus 10 roots equals 39. That's how he'd state a problem. And then he'd walk you through the solution, step by step, in prose. And you might think, well, that sounds clunky, and it is, compared to what we have now. But think about what he was doing. He was trying to create a universal framework. He wasn't saying, here's a trick for this particular problem. He was saying, here's a method for every problem that looks like this. That's a conceptual leap. That's moving from arithmetic, calculating specific answers, toward algebra, understanding the structure of equations themselves. He also included geometric proofs for his methods. When he showed you how to solve a quadratic equation by completing the square, which is essentially what his method amounted to, he didn't just give you the recipe. He drew a square, added rectangles to it, and showed you geometrically why the method works. So he was bridging the Greek geometric tradition and the Indian computational tradition. He was standing at a crossroads, pulling from both directions, and creating something that was neither purely Greek nor purely Indian, but something new. And his other major contribution, the one that gave us the word algorithm, was a separate book, now mostly lost in its original Arabic form, but surviving in Latin translation, That explained the Indian decimal number system to an Arabic-speaking audience, how to write numbers using 9 digits and a 0, how to add, subtract, multiply, and divide using these symbols, how to work with fractions. Essentially, he was writing a user's manual for the number system that would eventually conquer the world. And it did conquer the world, but slowly, very slowly. We'll come back to that. Al-Khwarizmi wasn't working alone, of course. The House of Wisdom was full of brilliant minds. There was Al-Kindi, sometimes called the first Arab philosopher, who also wrote on mathematics and cryptography. In fact, his work on frequency analysis for breaking codes is one of the earliest known descriptions of cryptanalysis. There was the Banu Musa brothers, 3 siblings who wrote on geometry and mechanics, and even designed automata, mechanical devices, early robots, almost, powered by water and clever gear systems. The intellectual environment in 9th century Baghdad was extraordinary. It was one of those rare moments in history when political stability, economic prosperity, and cultural openness all aligned to create an explosion of knowledge. But let's follow the mathematical thread forward, because the Islamic world's contributions to mathematics didn't stop with Al-Khwarizmi, not even close. About a century and a half later, around 975 CE, a mathematician named Abu al-Wafa al-Buzjani was working in Baghdad, and he made significant advances in trigonometry. Remember how we talked about Hipparchus and Ptolemy developing chord tables? Well, Indian mathematicians had already moved from chords to sines, which was a more efficient way of doing trigonometry. Abu al-Wafa took it further. He introduced the tangent function into trigonometric tables and developed highly accurate sine tables. He also proved identities, relationships between trigonometric functions, that were essential for astronomy and would eventually become essential for everything from navigation to physics to electrical engineering. And then there's Omar Khayyam. You probably know that name. Most people in the English-speaking world know Omar Khayyam as a poet. The Rubaiyat, translated by Edward Fitzgerald in the 19th century, is one of the most famous collections of verse in the English language. A jug of wine, a loaf of bread, and thou. That Omar Khayyam. But here's the thing. Omar Khayyam was, first and foremost, a mathematician, a seriously brilliant one. Working in Persia in the late 11th century, around 1070 to 1100 CE, he made breakthroughs that wouldn't be matched in Europe for 500 years. His great mathematical work was a treatise on algebra, where he systematically classified and solved cubic equations. That's equations where the highest power is 3, like x cubed. Now, Al-Khwarizmi had dealt with quadratics, x squared. Khayyam went 1 degree higher, and the difficulty escalates enormously. He couldn't solve cubics with pure algebra the way we can today. What he did instead was find solutions using the intersections of conic sections, parabolas, hyperbolas, circles. He would set up 2 curves, find where they crossed, and that intersection point gave him the solution to the cubic equation. It was geometric algebra at its most sophisticated, a technique that echoed Apollonius and Archimedes, but went beyond anything the Greeks had done. And Khayyam knew he hadn't finished the job. He wrote, with remarkable honesty, that he hoped future mathematicians would find purely arithmetic solutions to cubics, solutions using numbers and operations rather than geometric constructions. And they would, eventually. But it would take until the 16th century in Renaissance Italy. And the story of how that happened is one of the wildest tales in the history of mathematics. We'll get there. Khayyam also did important work on the parallel postulate, Euclid's 5th postulate, the one we flagged earlier as being different from the others, the one that felt less self-evident. Khayyam tried to prove it from the other four postulates, and in doing so, he explored what would happen if it weren't true. He didn't realize it, but he was taking the first steps toward non-Euclidean geometry, a revolution that wouldn't fully arrive for another 700 years. Sometimes mathematics is like that. Someone opens a door, peers through it, doesn't quite understand what they're seeing, and walks away. And centuries later, someone else walks through that same door and discovers an entire universe on the other side. Now, while all of this was happening in the Islamic world, what was going on in Europe? Well, for a long time, not much. At least, not in mathematics. The early medieval period in Western Europe, roughly the 5th through 10th centuries, was a time of political fragmentation, economic contraction, and limited intellectual exchange. The great Greek texts were largely unavailable. Most educated Europeans knew some basic arithmetic and geometry, enough for commerce and land measurement, and calculating the dates of Easter. But the deep mathematical traditions of Greece and India and the Islamic world were simply unknown to them. They were still using Roman numerals, still working with clunky computational methods, still operating in a mathematical world that was, frankly, impoverished compared to what was flourishing in Baghdad and Cairo and Cordoba. But that began to change, and it changed through contact. Spain was the crucial gateway. The Iberian Peninsula had been partly under Islamic rule since 711 CE, and cities like Toledo and Cordoba were centers of learning where Arabic, Latin, Hebrew, and Romance languages all mingled. In the 12th century, a wave of translation activity swept through Toledo especially as European scholars, many of them clergy, began systematically translating Arabic texts into Latin. And through those translations, Europe rediscovered Euclid, encountered Ptolemy's Almagest, and, crucially, met al-Khwarizmi's algebra and the Indian Arabic number system for the first time. One of the most important figures in this transmission was an Italian, Leonardo of Pisa, better known by his nickname Fibonacci. Born around 1170, he grew up partly in North Africa, where his father was a customs official for the Republic of Pisa. And in North Africa, the young Leonardo encountered the Hindu-Arabic numeral system and was immediately struck by how vastly superior it was to the Roman numerals used back home. He traveled widely, Egypt, Syria, Greece, Sicily, studying with mathematicians, learning different computational traditions. And in 1202, he published a book called Liber Abaci, the Book of Calculation. Now, Fibonacci is famous today mostly for the Fibonacci sequence, that pattern where each number is the sum of the two before it, 1, 1, 2, 3, 5, 8, 13, and so on. And yes, that sequence appears in the Liber Abaci as part of a problem about breeding rabbits. But the Fibonacci sequence is actually a tiny footnote in the book. The real importance of the Liber Abaci was much bigger than that. It was a comprehensive introduction to the Hindu-Arabic numeral system for a European audience. It showed merchants, bankers, and scholars how to calculate using these new numerals, how to do arithmetic, how to convert currencies, how to calculate profits and interest, how to solve practical commercial problems. It was, in a sense, al-Khwarizmi's work repackaged for medieval Italy. And it worked. Slowly, over the next few centuries, the Hindu-Arabic numerals spread through Europe. Not without resistance, mind you. Some cities actually banned the new numerals for a while, worried that the zero could be too easily altered to look like other digits, making fraud easier. Imagine that, banning a number system because zero was too dangerous. But convenience won out, as it usually does. By the 15th century, The new numerals were standard across European commerce and scholarship, and the stage was set for a mathematical explosion. But before that explosion happened in Europe, let's pause and acknowledge something. The transmission of mathematical knowledge from the Islamic world to Europe is one of the most consequential knowledge transfers in human history. Without it, the scientific revolution might not have happened, or at least not when and where it did. The algebra, the number system, the trigonometry, the preserved Greek texts, all of it flowed through Arabic-speaking scholars who didn't just pass it along, but enriched it enormously in the process. Al-Khwarizmi, Omar Khayyam, Abu al-Wafa, and dozens of others weren't just custodians of ancient knowledge. They were creators of new knowledge. And the fact that their contributions are sometimes overlooked in Western accounts of mathematical history is a loss, because the story doesn't make sense without them. The thread breaks. So now we're in Europe, and it's the late medieval and early Renaissance period, and mathematics is waking up. The Hindu-Arabic numerals are spreading. Algebra is becoming known. And in the universities that are springing up across Europe, Bologna, Paris, Oxford, Cambridge, scholars are beginning to engage seriously with mathematical ideas for the first time in centuries. But the really dramatic story, the one that signals the beginning of a new era in mathematics, happens in 16th century Italy, and it involves cubic equations, public duels, secret formulas, broken promises, and some of the most colorful characters in the entire history of mathematics. So let's dive in. The problem of the cubic equation, that is, an equation where the highest power of the unknown is 3, like x cubed plus some x's plus some number equals 0, had been lurking around for centuries. Omar Khayyam, as we talked about, had found geometric solutions using intersecting conic sections, but he'd openly wished for a purely algebraic answer, a formula that would just spit out the solution the way the quadratic formula handles second-degree equations. Nobody had found one, and by the early 1500s in Italy, finding such a formula was considered one of the great open problems in mathematics. Now, here's the cultural context you need to appreciate. In Renaissance Italy, mathematics wasn't just an academic pursuit. It was a competitive sport. Literally, mathematicians would challenge each other to public contests. You'd each submit a list of problems to your opponent, and whoever solved more problems in the allotted time won. The loser might forfeit money, but more importantly, they'd forfeit reputation. And reputation was everything. Your ability to attract students, to secure university positions, to win patronage from wealthy families. All of it depended on your standing in these intellectual duels. So mathematicians guarded their best techniques the way a swordsman guards his secret moves. You didn't publish your discoveries. You hoarded them. You kept them as weapons for the next contest. Into this world steps a professor at the University of Bologna named Scipione del Ferro. Sometime around 1515 or so, Del Ferro figured out how to solve one particular type of cubic equation, what was called the depressed cubic, where there's no x squared term. He found an actual algebraic formula, and this was a monumental breakthrough. But did he publish it? No. He kept it secret for years. He only shared it near the end of his life with a student named Antonio Fior, and Fior, who was apparently not the most talented mathematician himself, now possessed this incredible secret weapon without fully understanding its depth. Meanwhile, in another part of Italy, there was a man named Niccolò Fontana, though history remembers him by his nickname, Tartaglia, which means the stammerer. And his story is heartbreaking and remarkable in equal measure. When Tartaglia was about 12 years old, French soldiers sacked his hometown of Brescia in 1512. A soldier slashed the boy across the face with a saber, cutting through his jaw and palate. He nearly died. The wound left him with a severe speech impediment for the rest of his life, hence the cruel nickname. His family was too poor to afford more than a handful of days of formal schooling. Tartaglia was essentially self-taught. He learned mathematics on his own, working his way up from basic arithmetic to the frontiers of algebra through sheer determination and brilliance. By the 1530s, Tartaglia had become a respected mathematician, and word reached him that Fior was going around boasting that he could solve cubic equations. A challenge was arranged. Fior sent Tartaglia 30 cubic equations. Tartaglia sent Fior a mix of different problems. And here's the thing. In the days leading up to the contest, Tartaglia didn't actually know how to solve cubics. He was working on it frantically. And then, on February 13th, 1535, in a flash of insight, he figured out the method. Not just for the one type that Del Ferro had solved, but for a broader class of cubics. He solved all 30 of Fior's problems in just 2 hours. Fior couldn't solve a single one of Tartaglia's. It was a rout. Now Tartaglia was the man of the hour, the mathematician who could crack cubics. And this attracted the attention of one of the most fascinating and controversial figures in Renaissance intellectual life, Girolamo Cardano. Cardano was a physician, mathematician, astrologer, gambler, and writer who lived one of the most dramatic lives of the 16th century. He was brilliant, ambitious, and deeply complicated. He wrote one of the first serious works on probability theory, inspired by his own gambling habit. He cast horoscopes for royalty. He was eventually arrested by the Inquisition for heresy, for casting a horoscope of Jesus Christ of all things. His eldest son was executed for poisoning his own wife. Cardano's life reads like a novel. Cardano desperately wanted Tartaglia's cubic formula. He begged, he flattered, he promised. And eventually, in 1539, Tartaglia relented. He shared his method with Cardano, but on one condition: Cardano had to swear an oath never to publish it. Cardano agreed. He swore the oath. And then he broke it. Well, it's more complicated than that. And this is where the moral ambiguity gets interesting. Cardano and his brilliant young student, Lodovico Ferrari, continued working on the problem. Ferrari, who was astonishingly talented, Cardano had discovered him as a teenage servant in his household and recognized his mathematical gifts, actually managed to solve the quartic equation, the fourth-degree equation, by reducing it to a cubic. But you couldn't publish the quartic solution without revealing the cubic method, because the quartic depended on it. Then, Cardano learned that Del Ferro had actually discovered the cubic formula before Tartaglia. He traveled to Bologna and examined Del Ferro's original notes, which had been preserved by Del Ferro's son-in-law. This gave Cardano what he felt was a justification. The method wasn't solely Tartaglia's discovery, so the oath perhaps didn't apply. In 1545, Cardano published his masterwork, the Ars Magna, the Great Art, which contained the cubic formula, the quartic formula, and a wealth of algebraic insight that was decades ahead of its time. Tartaglia was furious. He felt utterly betrayed. A bitter public feud erupted. Tartaglia challenged Cardano to a mathematical duel, but it was Ferrari who showed up to fight on Cardano's behalf. The contest took place in Milan in 1548, and Ferrari won decisively. Tartaglia's reputation never fully recovered. He died in relative obscurity in 1557, still bitter about what he saw as the theft of his greatest discovery. Now, here's why the Ars Magna matters beyond the drama. The cubic formula itself is actually kind of unwieldy. It's much more complicated than the quadratic formula, and practicing mathematicians rarely use it directly. But the process of finding it forced Cardano and his contemporaries to confront something deeply unsettling. When you apply the cubic formula to certain equations that you know have perfectly real, ordinary solutions, the formula sometimes produces expressions involving the square roots of negative numbers, the square root of -1, which at the time made no sense whatsoever. What number, multiplied by itself, gives you -1? There isn't one. Not among any numbers anyone had ever imagined. Cardano called these quantities sophistic and, as subtle as they are, useless. But he noticed that if you just held your nose and kept calculating with them, treating them as if they were real, the weird square roots of negative numbers would sometimes cancel out at the end, leaving you with a perfectly valid real answer. It was like walking through a room that shouldn't exist to get to a door on the other side. The room was impossible, but the door was real. This was the first appearance of what we now call imaginary numbers and complex numbers, and it would take mathematicians centuries to fully make peace with them. Raffaele Bombelli, an Italian engineer working a few decades after Cardano, was the first to take these strange quantities seriously and develop systematic rules for calculating with them. He published his algebra in 1572, and in it he laid out how to add, subtract, and multiply expressions involving the square root of -1. He didn't fully understand what these numbers meant. Nobody did. Not yet. But he showed that they worked. They were useful. They gave correct answers. And here's what's remarkable. These imaginary numbers, born from a purely algebraic puzzle about cubic equations in 16th century Italy, would turn out to be absolutely fundamental to modern physics and engineering. Today, complex numbers are essential in electrical engineering, quantum mechanics, signal processing, fluid dynamics, you name it. Every time an electrical engineer analyzes an alternating current circuit, they're using complex numbers. Every time a physicist writes down the Schrödinger equation, which is the foundational equation of quantum mechanics, there's an I sitting right there. The square root of -1, built into the fabric of reality at its deepest level. Cardano would have been astonished. So the cubic equation saga gave us more than a formula. It gave us a glimpse of a larger mathematical universe, one where numbers didn't have to be things you could count on your fingers or measure with a ruler. Numbers could be abstract, strange, seemingly impossible, and still be true, still be useful. That's a profound shift in what mathematics is. And the Ars Magna did something else too. It marked the moment when European mathematics began to surpass the achievements of the ancient Greeks and the Islamic algebraists. For the first time, European mathematicians had solved problems that no one in history had solved before. The cubic and quartic formulas went beyond anything in Euclid, beyond anything in Al-Khwarizmi or Omar Khayyam. A door had opened, and the next 2 centuries would see an absolute torrent of new mathematics pouring through it. But before we get to the 17th century and the invention of calculus, which is really the next giant leap, there's another thread we need to pick up, and it involves a French lawyer who did mathematics in his spare time. His name was François Viette, and what he did with notation changed everything. Viette was working in the late 1500s, and he had this beautifully simple idea that seems obvious in hindsight, but was genuinely revolutionary at the time. He started using letters to stand for unknown quantities and for known constants in equations. Now, you might be thinking, wait, didn't algebra already use unknowns? And yes, it did. Al-Khwarizmi talked about the thing and the square of the thing, and later, mathematicians used abbreviations and shorthand. But Viette took it further. He introduced a systematic practice of using vowels like A, E, I for unknowns and consonants like B, C, D for given quantities. And what that meant was that for the first time, you could write down a general equation, not just find the number whose square plus 5 times itself equals 24, but something like a squared plus B times A equals C, where B and C could be anything. You could manipulate the equation as a general form. You could prove things about entire families of equations all at once, rather than solving them one specific case at a time. This is one of those moments where notation doesn't just record mathematics. It actually creates new mathematics. Before Viette, every algebraic problem was essentially a word problem. After Viette, algebra started to look like algebra, the way you remember it from school. That symbolic language, that ability to push letters around on a page according to rules, that was Viette's gift. And it opened up enormous new territory, because suddenly you could see structural patterns that were invisible when everything was written out in words. He published his key work called In Artem Analyticum Isagoge, Introduction to the Analytic Art, in 1591, and it's really the birth of symbolic algebra as we know it. And here's the thing about notation. It's tempting to think of it as just cosmetic, just a way of writing things down more neatly. But it's so much more than that. Good notation is a thinking tool. It compresses ideas so that your mind can hold more of them at once. It reveals analogies. It makes certain manipulations almost automatic, things that would have been incredibly laborious in words. Think about how hard long division would be if you had to do it in Roman numerals. Same principle, but at a much higher level of abstraction. Viette's notation was a lever for the mind, and the mathematicians who came after him, Descartes, Fermat, Leibniz, Newton, all built on that lever. Speaking of Descartes, let's talk about René Descartes, because what he did in 1637 is one of the most elegant mergers in all of mathematical history. Descartes was a philosopher, of course. I think, therefore I am, and all that. But he was also a first-rate mathematician, and in an appendix to his philosophical work, Discourse on the Method, he included a piece called La Géométrie, and in it, he did something that would have stunned the ancient Greeks. He married algebra and geometry. He showed that you could take a geometric curve, a circle, a parabola, an ellipse, any curve you like, and describe it with an algebraic equation. And conversely, you could take any equation and see it as a shape, a curve, a geometric object. This is what we now call the Cartesian coordinate system, that grid with an x-axis and a y-axis that you've been drawing since middle school. That's Descartes, and the power of it is hard to overstate. Before Descartes, geometry and algebra were essentially separate disciplines. Geometry was about shapes and space and visual reasoning, the way the Greeks did it. Algebra was about equations and unknowns, the way the Islamic mathematicians and the Italian algebraists did it. They were two different languages for two different kinds of problems, and Descartes built a bridge between them. Now, a geometric question. What's the shape of this curve? Where does it intersect that line? Could be answered with algebraic calculation. And an algebraic question. What does this equation look like? What are its properties? Could be visualized as geometry. Two entire branches of mathematics suddenly became one. And remember those conic sections from Apollonius, way back in ancient Greece? The ellipses and parabolas and hyperbolas that he studied purely as geometric objects, slicing cones with planes. Now, in Descartes' framework, each of those curves had a simple algebraic equation. An ellipse is x squared over a squared plus y squared over b squared equals 1. A parabola is y equals x squared. These shapes that Apollonius had spent his life cataloging could now be captured in a few symbols. And more importantly, you could discover new curves that the Greeks never imagined, just by writing down new equations and asking what shape they described. Now, around the same time Descartes was doing this in France, there was another Frenchman working on related ideas, and his name was Pierre de Fermat. Fermat is famous today mostly for one thing: Fermat's last theorem, that maddening marginal note where he claimed to have a proof that was too large to fit in the margin. We'll come back to that. But Fermat was also independently developing coordinate geometry, possibly even before Descartes, though he didn't publish as aggressively. And Fermat did something else that's crucial to our story. He figured out a method for finding the maximum and minimum values of curves, the peaks and valleys. His technique involved looking at what happened when you made a tiny change to the input and asked when the output stopped changing. If that sounds familiar, it should, because it's essentially the core idea of differential calculus. Fermat was doing proto-calculus in the 1630s, decades before Newton and Leibniz formalized it. And this is important because it shows you that calculus didn't spring fully formed from the minds of Newton and Leibniz. It had been brewing for a long time. Archimedes had the seeds of it 2,000 years earlier, with his method of exhaustion. Fermat had pieces of the derivative. Another mathematician, Bonaventura Cavalieri, was developing ideas about integration, adding up infinitely thin slices to find areas and volumes. In Italy, in the 1630s, Isaac Barrow, who was actually Newton's teacher at Cambridge, proved a version of what we now call the fundamental theorem of calculus, linking the two operations of differentiation and integration. The ingredients were all there, scattered across Europe, waiting for someone to put them together into a coherent system. And then, in the 1660s and 70s, two men did exactly that, independently, and the result was one of the most bitter priority disputes in the history of science. Isaac Newton, working in England, developed what he called the method of fluxions, starting around 1665 and 1666, during those famous plague years when Cambridge University closed and Newton retreated to his family home in Woolsthorpe. He was in his early 20s. And in that isolation, he didn't just invent calculus. He also developed his theory of gravity and did groundbreaking work on optics. It's one of the most extraordinary bursts of creative output any human being has ever produced. But Newton was secretive, almost pathologically so. He didn't publish his calculus for decades. He wrote it up in manuscripts that circulated among a small circle of English mathematicians, but he didn't put it into print. Meanwhile, in Germany, Gottfried Wilhelm Leibniz independently developed his own version of calculus in the mid-1670s, and he published it in 1684 and 1686. Leibniz's notation was different from Newton's, and here's where the Viet thread comes back. Leibniz's notation was better. Much better. The dx and dy notation, the integral sign that looks like an elongated S for summa, the way you can manipulate differentials almost like fractions, that's all Leibniz. Newton's dot notation worked fine for physics problems involving time, but Leibniz's notation was more flexible, more generalizable, more conducive to the kind of algebraic manipulation that would drive mathematics forward. And this is yet another case where notation shaped the future of an entire field. Continental European mathematicians adopted Leibniz's notation and raced ahead, while British mathematicians, loyal to Newton, clung to his notation and fell behind for nearly a century. But the priority dispute itself was ugly. By the early 1700s, accusations were flying. Newton's supporters claimed Leibniz had stolen the ideas during a visit to London in 1676, where he might have seen some of Newton's unpublished manuscripts. Leibniz's supporters countered that Leibniz had developed his methods independently, which the historical evidence strongly supports. The Royal Society in London conducted an investigation in 1712, but Newton essentially wrote the report himself, and unsurprisingly, it concluded that Newton had priority. Leibniz died in 1716, somewhat disgraced in England, though celebrated on the continent. It was a tragedy, really. Two brilliant men whose combined contributions gave humanity one of its most powerful intellectual tools, and instead of celebrating each other, they spent their later years in bitter recrimination. So, what actually is calculus, and why does it matter so much? Let me put it as simply as I can. Calculus is the mathematics of change. Everything in the physical world that moves, grows, shrinks, speeds up, slows down, oscillates, flows, or evolves, calculus is the language that describes it. It comes in two flavors. Differential calculus asks, how fast is something changing right now, at this exact instant? What's the slope of this curve at this precise point? And integral calculus asks the reverse. If I know how fast something is changing at every moment, can I add all those tiny changes up to find the total? What's the area under this curve? And the deep, beautiful insight, the fundamental theorem of calculus, is that these two operations are inverses of each other. Differentiation and integration undo each other, the same way addition and subtraction do, or multiplication and division. That connection, that bridge between the local question of how fast and the global question of how much, is what makes calculus so extraordinarily powerful. It's why Newton could use it to derive the orbits of planets from his law of gravity. It's why engineers use it to design everything from airplane wings to electrical circuits to the algorithms that route data across the internet. And once calculus existed, mathematics exploded. The 18th century saw an astonishing acceleration, driven largely by one family and one man. The family was the Bernoullis, a Swiss dynasty that produced at least 8 significant mathematicians across 3 generations, which is remarkable and also apparently made for incredibly tense family dinners. Johann Bernoulli and his brother Jakob feuded bitterly over mathematical problems, and Johann later feuded with his own son Daniel, even trying to plagiarize Daniel's work on hydrodynamics. But their contributions were immense. The calculus of variations, probability theory, fluid dynamics, the mathematics of elasticity. And then there was Leonhard Euler, who had studied under Johann Bernoulli and who became arguably the most prolific mathematician in all of history. Euler was born in Basel, Switzerland in 1707, and over the course of his career, he produced roughly 800 papers and books, touching virtually every branch of mathematics that existed in his time and creating several new ones. He standardized much of the notation we still use today, the function notation f of x, the use of e for the base of the natural logarithm, the use of pi for the ratio of a circle's circumference to its diameter, the use of I for the square root of -1. Remember Bombelli's strange arithmetic with those impossible square roots of negative numbers? Euler gave that square root of -1 its name and its symbol, and he discovered what many mathematicians consider the most beautiful equation in all of mathematics. E to the power of I times pi plus 1 equals 0. 5 of the most fundamental constants in mathematics, E, I, pi, 1 and 0, linked together in a single, simple equation. It's almost eerie in its elegance. Euler went blind in one eye in his 30s and completely blind in his 70s, and his productivity barely slowed. He dictated papers to his sons and assistants, holding enormous calculations in his head. When he died in 1783, he left behind such a backlog of unpublished work that the St. Petersburg Academy continued publishing his papers for nearly 50 more years after his death. And Euler didn't just do pure mathematics. He worked on mechanics, astronomy, optics, acoustics, the theory of music, shipbuilding, even the design of lenses for telescopes. He was the bridge between the invention of calculus and the explosion of mathematical physics that would define the 19th century. And that 19th century is where things get really interesting, because it's when mathematicians started asking dangerous questions about the foundations of everything they'd been doing. Questions like, what exactly do we mean by infinity? What do we mean by a continuous function? What do we mean by a number? These sound like philosophical navel-gazing, but they turned out to be the most important questions in the history of mathematics. Because when you poke at those foundations, when you really demand precise answers, you either find bedrock or you find cracks. And what 19th century mathematicians found was both. Let's start with that word, continuity. Calculus, as Newton and Leibniz and Euler practiced it, worked brilliantly. It gave correct answers. It predicted the motions of planets, the shapes of vibrating strings, the flow of heat through metal. But if you pressed on the logic underneath, things got uncomfortable. What exactly was an infinitesimal? A quantity smaller than any positive number, but not zero. That doesn't really make sense, does it? Bishop Berkeley, an Irish philosopher, had mocked Newton's infinitesimals as ghosts of departed quantities back in 1734. And honestly, he had a point. The calculus worked, but nobody could explain rigorously why it worked. It was like a magnificent cathedral built on a foundation that, when you looked closely, seemed to be hovering slightly above the ground. So in the early 1800s, a French mathematician named Augustin Louis Cauchy set out to fix this. Cauchy was a fascinating character, devoutly Catholic, politically conservative, stubborn to the point of infuriating his colleagues, and extraordinarily productive. He published nearly 800 papers in his lifetime, and what Cauchy did was begin replacing the vague language of infinitesimals with the precise language of limits. Instead of saying a quantity becomes infinitely small, Cauchy said, a sequence approaches a limit L if, for any margin of error you care to name, however tiny, there's a point in the sequence beyond which every term stays within that margin of L. No infinitesimals needed, no ghosts, just a careful logical statement about ordinary numbers. This might sound like a small thing, but it changed everything. It meant you could finally define what it meant for a function to be continuous. Roughly, a function is continuous if small changes in the input produce small changes in the output, made precise through that same limit language. And you could define what it meant for a series to converge, what it meant for a derivative to exist. Cauchy didn't finish the job entirely. That fell to Karl Weierstrass, a German mathematician working a generation later, who refined Cauchy's definitions into the rigorous epsilon-delta framework that every calculus student still encounters today. Weierstrass was a late bloomer, by the way. He spent years as a secondary school teacher, teaching mathematics to teenagers while doing revolutionary research on the side. He didn't get a university position until he was 40. But when he did, his lectures in Berlin became legendary. He showed that some continuous functions are nowhere differentiable. Imagine a curve that's connected, with no breaks, but so jagged at every single point that you can never draw a tangent line anywhere. It's continuous, but has no slope, anywhere. That's deeply counterintuitive. It disturbed people. Even some mathematicians found it unsettling, almost pathological. But it was true, and it showed that the naive picture of what a curve looks like was far too limited. Now, while Cauchy and Weierstrass were tightening up the foundations of calculus, something even more revolutionary was happening in geometry. Remember Euclid's fifth postulate, the parallel postulate, the one that felt different from the others, the one that Omar Khayyam and many others had tried to prove from the first four? Well, in the early 19th century, 3 mathematicians independently reached a stunning conclusion. You can't prove it, because it's not a necessary truth. You can replace it with a different postulate and get a perfectly consistent, perfectly logical geometry that simply describes a different kind of space. The 3 were Carl Friedrich Gauss, János Bolyai, and Nikolai Lobachevsky. Gauss was already the most famous mathematician in Europe. People called him the Prince of Mathematicians. But he was cautious, even secretive, and he never published his ideas about non-Euclidean geometry. He feared the controversy. Bolyai was a young Hungarian officer, the son of a mathematician who had himself spent years trying to prove the fifth postulate and had begged his son not to waste his life on it. The son didn't listen. In 1832, Bolyai published a 26-page appendix to one of his father's books, laying out a geometry in which, through a given point, infinitely many lines can be drawn parallel to a given line. When his father sent the work to Gauss, Gauss replied that he couldn't praise it because that would be praising himself. He'd had the same ideas for decades. Bolyai was devastated. He suspected plagiarism and never really recovered his mathematical ambition. Meanwhile, Lobachevsky, working independently in the Russian city of Kazan, published similar results starting in 1829, largely unnoticed by Western Europe for years. Think about what this meant. For over 2,000 years, Euclid's geometry had been considered the geometry, the true description of the space we live in. And now, suddenly, there were alternatives. Geometries where the angles of a triangle add up to less than 180 degrees or more than 180 degrees. Geometries where space itself curves. It sounds abstract, but here's the punchline. When Einstein developed his general theory of relativity in 1915, the mathematics he needed to describe how mass warps space-time was exactly this non-Euclidean geometry, refined by Bernhard Riemann in the 1850s. Riemann, in a single legendary lecture in 1854, generalized the whole idea of geometry to spaces of any number of dimensions with any kind of curvature. He was 37 when he died of tuberculosis, but that one lecture reshaped mathematics and, 60 years later, physics. Pure mathematical curiosity. What happens if we change one axiom? Turned out to describe the actual structure of the universe. That thread we've been following, where abstract mathematics unexpectedly becomes the language of physical reality, it runs right through here. And then there's the question of infinity. Georg Cantor, working in the 1870s and 1880s, did something nobody had dared to do before. He treated infinity not as a vague concept meaning goes on forever, but as a precise mathematical object that could be studied, compared, and measured. And what he discovered was breathtaking. He proved that there are different sizes of infinity. The infinity of counting numbers 1, 2, 3, 4, on and on, is the smallest kind of infinity. The infinity of real numbers, all the points on a number line, including all the irrational numbers like the square root of 2 and pi, is a strictly larger infinity. There are more real numbers between 0 and 1 than there are counting numbers in the entire infinite sequence. His proof is beautiful, by the way. It's called the diagonal argument, and it works by contradiction. You assume you can list all the real numbers between 0 and 1. Then you construct a new number that differs from every number on your list in at least one decimal place. So your list can't be complete. Therefore, the real numbers are uncountable. It's one of those arguments that, once you see it, feels almost inevitable. Cantor's work was met with fierce opposition. Leopold Kronecker, one of the most powerful mathematicians of the era, called Cantor a corrupter of youth and tried to block his publications. Henri Poincaré called set theory a disease from which mathematics would eventually recover. Cantor suffered severe bouts of depression throughout his life, spent time in sanatoriums, and died in poverty in 1918. But he was right. His set theory became the foundation on which virtually all of modern mathematics is built. Every mathematical object, numbers, functions, geometric spaces, can be described in the language of sets. It's the bedrock, but even that bedrock had cracks. In 1901, Bertrand Russell discovered a paradox at the heart of naive set theory. Consider the set of all sets that don't contain themselves. Does it contain itself? If it does, then by definition it doesn't. If it doesn't, then by definition it does. It's a logical contradiction, baked right into the foundations. This sent mathematicians into something of a crisis. David Hilbert, perhaps the most influential mathematician of the early 20th century, proposed an ambitious program. Formalize all of mathematics into a complete, consistent set of axioms, and prove that those axioms can never produce contradictions. It was a dream of perfect certainty, of putting mathematics on an unshakable foundation once and for all. And then, in 1931, a quiet 25-year-old Austrian named Kurt Gödel shattered that dream. Gödel's incompleteness theorems showed that in any consistent formal system powerful enough to describe basic arithmetic, there will always be true statements that cannot be proved within the system. Mathematics cannot fully validate itself. There will always be truths beyond the reach of any fixed set of rules. It's one of the most profound results in the history of human thought, and it came from a young man who was so shy and anxious that he could barely bring himself to present his findings at a conference. Gödel later fled Nazi-occupied Austria, ended up at the Institute for Advanced Study in Princeton, became close friends with Einstein, and grew increasingly paranoid in his later years, eventually refusing to eat for fear of being poisoned. He starved to death in 1978. The human stories in mathematics are sometimes unbearably poignant, but mathematics didn't stop. It couldn't. Gödel's result didn't mean mathematics was broken. It meant mathematics was inexhaustible. There would always be more to discover, more to prove, more to understand. And the 20th century bore that out spectacularly. Alan Turing, inspired partly by Gödel, formalized the concept of computation in 1936 with his theoretical Turing machine, laying the groundwork for every computer that would ever exist. John von Neumann took that theory and helped build actual machines. Claude Shannon used Boolean algebra, George Boole's 19th century formalization of logic into mathematical notation, to design the digital circuits that make modern electronics possible. Every time you tap your phone, you're using Boolean logic, running on a Turing-complete machine, processing information measured by Shannon's entropy. Mathematics isn't just describing the world anymore, it's building it. And here's where we can take a breath and look back at the whole arc. Because what you've been listening to, this long, winding story, it's really the story of one species slowly teaching itself to think abstractly. It started with a bone, maybe, with scratches on a wolf's fibula 30,000 years ago. Someone keeping count of something. Someone realizing that the idea of 3 exists apart from 3 deer or 3 days. It moved through clay tablets in Mesopotamia, through papyrus scrolls in Alexandria, through palm leaf manuscripts in India, through Arabic texts in Baghdad, through printed books in Renaissance Italy, through letters exchanged between rivals who couldn't stand each other, but couldn't stop pushing each other forward. And the beautiful thing, the thing that might stay with you as you drift off, is how connected it all is. Bombelli's strange imaginary numbers, born from a cubic equation puzzle in the 1500s, became Euler's transcendent identity, became the essential language of quantum mechanics 4 centuries later. Apollonius's study of conic sections, a purely geometric curiosity in ancient Greece, became the orbits of planets under Kepler, became the trajectories of spacecraft. Riemann's abstract curved spaces became Einstein's description of gravity. Cantor's infinite sets became the foundation of topology, which became essential to modern physics and data science alike. Again and again, mathematicians followed their curiosity into what seemed like pure abstraction, and the universe turned out to be waiting there. So if you're still listening and your eyes are getting heavy, let this be the thought you carry into sleep. Mathematics isn't something humans invented to make life difficult. It's something we discovered piece by piece over thousands of years, often by accident, often through failure, often through the stubbornness of people who couldn't let go of a question. And every piece turned out to connect to every other piece in ways nobody could have predicted. The tally marks on that ancient bone, the 0 that someone dared to name in India, the imaginary number that Bombelli refused to abandon, the curved space that Riemann dreamed up in a lecture hall. They're all part of the same story. Your story, really. The story of minds reaching for patterns in the dark and finding, over and over again, that the patterns reach back. And that's a good thought to fall asleep to.